Good afternoon. You're able to hear me?
Yes, sir.
Okay. So there's no echo or anything like that, right? Is this clear?
Yep.
Okay. So any doubts from the previous class?
Sir, few of
s-
the exercise problems you had mentioned, I was not able to solve. So, would we be discussing those in the class itself, or should we ask in the Google Classroom or somewhere?
Yeah, not in the class, outside class hours.
Okay.
Sir, I want to understand the intuition behind this probabilistic modeling. So, why exactly we do that when we have other methods?
When we have a method.
We have this, discriminative methods like we discussed before. What area this probabilistic modeling solves? What kind of problem?
Okay. So by the way, there is a confusion. Uh, Discriminative models are also probabilistic methods. Hello.
Yeah, the voice is breaking.
So is it clear now?
Yes.
Please don't confuse discriminative modeling with empirical risk minimization. Right? Discriminative models are also probabilistic models, a special case of probabilistic models. I have tried to clearly distinguish between all three of them. So let me revise whatever we have done towards the last lecture. Perhaps that will give you some clarity.
So before
Yes.
that, I had one question. So when you spoke about hinge loss, right? So you mentioned that the bad part of hinge loss is that it is not differentiable, and so we go with something called logistic loss. So I just want to understand, like when you say not differentiable, why is it bad? Hello.
Yeah, please go on.
Yes, sir.
Hello.
Sir. Yes, sir. I'll repeat my question. So actually,
Uh, so
yeah.
Yeah, non-differentiability, it is bad in the sense that if you try to optimize the loss, the corresponding optimization algorithms will be inherently slower in terms of rate of convergence. Okay, so it's hard to minimize non-differentiable problems. Of course, I also told you how to rewrite the ERM problem with hinge loss such that everything becomes nice linear inequalities and so on. But if you want to directly solve the problem, it leads to computational difficulties. So anyway, this is just an alternative, right? So the one of the problems with the non-differentiability is optimizing it. So whenever losses are non-differentiable, they are harder to optimize. Um, so as an alternative, we thought about logistic loss. So did I answer your question?
Yes, sir.
Okay, so if nothing else, then let's just revise this notion of probabilistic models and so on. So till now we were talking about only one kind of methodology, which is empirical risk minimization with an inductive bias. Okay. Now what is the story in this case? The story in this case, so by the way, so let's begin with supervised learning itself so that so in supervised learning, you assume the unknown concept is represented by a joint distribution of inputs and outputs from which your training data set is sampled. So MID samples, right? And then your objective goal in supervised learning is to find the base optimal function, which is defined as um, the minimizer of empirical risk, right? So the minimizer of the true risk, right? So fine. So this is what we called as the true risk, right? Okay, so the minimizer of the true risk is what we are in search for in supervised learning. Now, we commented that this goal is an impossible goal to achieve it accurately, because if I don't know the underlying distribution, so this expectation here is taken with respect to P star, right? So as long as P star is unknown, um, there's no hope to be able to solve this problem exactly. So there are various, methodologies, frameworks to approximately solve this problem. Broadly, there are three frameworks. Okay, one is what we used to call as non-probabilistic modeling. More specifically, empirical risk minimization with inductive bias. Okay, so this is, or in short, empirical risk minimization, right? And the next category is, then the next kind of methods are what are known as probabilistic modeling. Okay, so, and here there are two varieties. One is generative modeling and one is discriminative modeling. Okay. Okay, now what are the differences? Let us discuss again. So in ERM, what we do is we do two kinds of approximations. One is we say we try to approximate. So let me use different colors for different methods. So the first thing we do is we approximate this expectation by an average. That's the first idea. So g of xi comma yi, and then not only that, we also restrict our search to some function class or some inductive bias, capital G. Okay, so there are two things which we do. Okay, and the goal of this, so whatever we get here is G hat. So it's, let us call it G hat. So the minimizer as G hat, right? And what we are interested in ERM is to show that G hat is close to G star. That's our goal. Okay, so everybody till here agrees with me?
Yes, sir.
Yes.
Okay, so this is what we tried to show or argue for which kind of inductive biases, which kind of loss functions, if we choose, then G hat, in which sense it will be close to G star. We have discussed various, details till now. Okay, now, so in some sense, in ERM, so the first thing you have to understand is that is ERM is modeling. Essentially, it's modeling the base optimal directly. Okay, that means our inductive bias, what kind of functions it has? It has candidates for base optimal. So every function in inductive bias we are taking because we hope that the base optimal is one of those functions. That is our, so we are essentially modeling the base optimal directly, right? Okay, now the second observation which you have to do is even if you estimate G star very well, P star is still unknown. Okay, so I am not learning the underlying concept, and I don't need to learn. I'm not saying we have to learn the underlying concept. That is not the goal in supervised learning. The supervised learning goal is to retrieve Bayes optimal, and hence, you know, ERM methods, what do? They take a direct approach. They just discuss, they just model things that are necessary. That's all. What is necessary? Bayes optimal is to be found. That's the only necessary and insufficient goal. So they directly model it, and they do not worry about modeling or finding the unknown distribution, right? Now, whereas in probabilistic modeling, you take a entirely different approach. You say that, okay, let me write it here. So in probabilistic modeling, whether generative or discriminative, in both of these cases, what we will do is model P star directly. Directly or indirectly. If we do directly, it's called generative. Indirectly, it's called discriminative. Anyway, we'll see. So the idea is to model P star, and once P star is known, you estimate P star, model P star, and estimate it. Estimate P hat. So what's your hope? So your hope is that P hat is close approximation to P star. Okay. Once you have that, then you compute G star, the Bayes optimal, by directly solving this problem. And now this problem can be solved because you're assuming that, so you're basically replacing P star by P hat. Okay, and if P hat is known, if the distribution is known, then this expectation, the true risk, can be computed, and perhaps you can minimize the true risk, right? So the goal of computing G star, the finding G star, simply becomes a deduction in this case, right? So you reduce the value of G star, right? So at this broad level, everybody is clear with what is probabilistic modeling, or how is it different from the earlier case? Yes? No?
Yes, sir.
Okay. So
So, sir, in simple words, if I want to say, like in the empirical risk modeling minimization, we are assuming G to find out a relationship between Y and X, and in probabilistic modeling as well, we are, modeling the distribution, which again is a relationship between Y and X.
right. So in ERM, basically the relationship is deterministic because we are looking for functions, and whereas in this case the relationship is stochastic. That's one way of thinking about. That's why the name probabilistic models versus non-probabilistic models. Okay. But that's a very gross understanding. Essentially, this is the more finer understanding, that if you find P star, you can simply deduce G star. So there are two fundamentally different approaches: either find P star and hence find G star, or directly try to find G star. These are the two approaches. Okay, so these are these are probabilistic models which try to find P star, and these are empirical risk minimization methods, non-probabilistic. Nobody calls it non-probabilistic, but just for your understanding. Okay, so is that clear?
Yes.
Okay, so in the last class we already gave two examples of solving this problem. So of solving this problem. So we said in case of regression, if the loss is square loss, then the base optimal simply turns out to be, so the base optimal's estimate simply turns out to be the mean of the posterior, right? And then in case of 0, 1 loss in classification, the base optimal's estimate turns out to be the mode of p, p hat y given x, right? And then we commented that irrespective of what is the loss, invariably what you simply need is the posterior distribution, posterior likelihood. You actually don't need the joint likelihood. So we divided probabilistic models into two cases. One is where you model the entire joint. So you model the entire joint likelihood. In this case, estimating the joint likelihood is the first step from data. So this I did not teach you how to do. So this is what we will learn mainly in this lecture. So how do I estimate a likelihood function from samples generated from it? That's what we will learn mainly in this lecture, at least the first part of the lecture. The second step is from the estimated, let's call this p hat x comma y, and from the estimated p hat x comma y we will try to find out the posterior, and then from the posterior you will find out gx, right? So from the posterior you will find the approximation to the base optimal. So these are the three steps involved in generative modeling. Whereas in discriminative modeling, there is a fundamental difference again. You don't model the joint, you will model directly the posterior. Okay, somehow you will directly model the posterior. And so the first step is estimate the posterior. Okay, and second step is same. So from the posterior, you will get the base optimal, right? So this is same as this, and this is same as this. So there's one extra step in case of generative modeling, right? Now in case of, so how do you compare this to ERM? So in ERM, directly you will find this, right? So it's like ERM has one step, discriminative models have two steps, generative models have three steps. Okay, that's the difference between these three methods. So is first of all these three methods at this level of understanding, is it clear? What are the differences? Is it clear?
Yes.
Okay, so now somebody asked, why should we do this? I mean, what are the advantages and disadvantages? Now, the advantages and disadvantages will be clearer as we cover them, as you understand them. Once I give examples, they'll be more clear. But if I have to answer the question as of now, then I would say one advantage with probabilistic modeling is, suppose, just to give you an example, suppose my inputs are, this is the example we were giving all the time, some kind of medical reports, right? And then y is presence or absence of a disease, right? Now in this case, methods like ERM will basically, given a report, they will label it with disease or not. That's all ERM methods can do. But suppose if somebody asks the ERM modeling, whatever the answer given by ERM model, what is the probability that it is right? So what is the probability that X has disease? Okay. Then such questions cannot be answered by non-probabilistic models. Whereas in probabilistic models, whether it is discriminative or generative, always we will have access to, so always we will have access to the posterior, right? So from this I can always, so this is what, nothing but the probability of outcome given the input, right? So this is exactly the answer for this question, right? So such questions can be answered in probabilistic modeling. I'm not saying such questions, will be answered very well, will be answered with very high accuracy. That depends on how well you model. Okay. I'm just saying the model is capable of directly answering such questions, whereas non-probabilistic modeling by definition cannot answer such questions. Okay. For example, if somebody asks you, how much will it rain today? Right, so you will say will it rain today or not, somebody asks you, right? So the non probabilistic modeling will give an answer like yes it will rain or no it will not rain, whereas probabilistic models also can tell you whether it will rain or not, yes or no, but in addition to that they can also tell you what is the probability of rainfall today according to their understanding, according to the model's understanding. Okay, so of course that is only close to the true likelihoods, but nevertheless the answer can be given. So whoever asked this question, why probabilistic modeling, did I give one reason?
Yes, sir.
So logistic regression, for example, kind of gives a probability of which class it belongs to, right?
I mean, the way I presented it, it does not, right? So the logistic regression model we have presented in this course
Okay.
does not. But if you know logistic regression from some other course, yes, it does, because it carries the same name. So we did not do the probabilistic version of it. We only did the non-probabilistic version.
Okay.
In today's class, or maybe tomorrow, the next class, we will cover the probabilistic version of it, where it will give the notion of probability. Okay. So if you recall the way we presented logistic regression, where is probability? Nowhere, right? So it will just find you a value of the linear function that separates the points. That's all. So it's just another loss function that is a alternative for hinge loss. So there's no notion of probability anywhere. Any other questions? So in fact, you should be careful. So whoever asks this question, for each of the model which is famous, you will typically have 3 variants of it. Okay, and people use the same name for all the 3 variants. So depending on the context, you should understand which variant are they talking about. For example, linear regression, we covered it as a non-probabilistic model. In today's class itself, we'll cover it as a generative model, and hopefully we'll also cover it as a discriminative model. All 3 will give you, in general, different answers, but in some sense they are very related. That's why all the 3 have the same name. Everybody calls them linear regression. But you should carefully understand which variant of the linear regression you are talking about. Is it the generative version, is it the discriminative version, or the non-probabilistic version? The implications of the estimates as well as the implications of the estimates will vary depend on which variant it is. But there are very very close similarities, and that's the reason why people call them by the same name. Now if I have to explain all of that, we will have to cover some details. So for the time being, don't be, just stick to whatever we have covered in this course, then there'll be no confusion. So any other questions, please? Okay, so now let's focus on this problem for some time, right? So given data set, a set of samples from a distribution, how do I estimate the distribution? Okay, once I understand how to solve this problem, then we will also give examples of this step. Okay, and this we have already covered in previous class, right? So let's start with solving this problem. So once we understand this problem is even more complicated. Okay, so that we will cover later on. Okay, so let's begin by solving this sub problem. So what is the sub problem? So you have some unknown distribution, and you have m samples from it, xi, yi, xm, ym, and your goal is to estimate this distribution from purely from these samples, and let's assume IID samples, right? Just for notational convenience, let me call x comma y as z. So it's as if, there is unknown distribution over z and there are samples z1 to zm. So whether I call it as z or x, it does not matter. Okay, so let me try to, and after we solve this problem, we'll worry about the other steps in generative modeling. Okay. Now, if I were to solve this problem, and if I were to mimic the steps in case of ERM, so let me write what we did in case of ERM. That's the only thing we did till now. And whenever we achieve, we learn something, we try to reuse it, right? So let's try to reuse our learning in case of ERM with inductive bias. Okay, and let's try to solve this problem of estimating P star given the samples using similar ideas. Okay, what did we do in case of ERM? First of all, we said we identified the goal. The goal was to find a G, that kind of minimizes the loss between gx and y. And then we said this should hold for this x and y are not fixed quantities, they come from a distribution. So actually your goal is to minimize this. That's what we said. And then we went on to said, minimizing this does not make sense because it's a random variable. So we'll instead minimize the expected loss. So that was called the risk. And then we said this goal is impossible to solve. So we'll do, we'll go with the following approximation of approximating the sample mean by the true mean by the sample mean. And then we realize this does not work. We have to have some inductive bias, right? So this was the story in case of ERM. Okay, and we'll try to apply similar ideas and try to rephrase the problem which we have here. Okay. Now, what is our goal here? Of course, to find a distribution, a likelihood P, right? And how should we say, and what is our goal? P should be close to L, P should be close to P star. And similarly, like we chose a way of saying, so how did we say Gx is close to Y? We introduced this notion of loss function, right? So let me introduce the notion of loss function again. What does this loss function do? It will tell me how close P and P star are. So this is a different kind of loss function. So it's yet another loss function. Okay, don't think it is same as the previous L. So let me call it L dash or something. Okay, so what does the usual loss function do? It will tell me how close g of x and y are, or in general it will tell me how close two outputs are. Whereas this fellow, it takes as input two distributions. It does not take function evaluations. It takes two distributions and says how close they are. Okay. So what is your ideal goal? Your ideal goal is to solve this problem, right? So minimize P out of all distributions. You want to find that P where the loss between this and this is minimum, right? And hopefully your answer will be, if you take a reasonable enough loss function L dash, your answer for this problem will be same as P star. Okay, so are we clear? We just rewrote the problem as an optimization problem. So is this clear to everybody?
Yes, sir.
Okay, now there are two issues with this. One is, again, we have to understand which loss function will we use. So previously we gave many examples of loss functions. Like this, we have to give many examples of loss functions here. Secondly, this directly involves P star, right? So P star is unknown, which is unknown. So that's the difficulty, that's the challenge, right? So what is the information given to you? Only samples from P star, not P star. So how did we get around this problem in case of ERM? In case of ERM, somehow we had this expectation sitting in our optimization problem very naturally, right? And then it was very natural to think about approximating the expectation by the average, right? Which we knew that by law of large numbers, they will be close for any particular G, right? So essentially, what helped the day in case of ERM is, this expectation being a part of my objective, right? Whereas here, there's no expectation term. So I don't know how to, go about solving this. Okay, so this is one problem. Now let's discuss what loss functions are there. Okay. Now there are some two very important loss functions which are useful for us. We'll just write them. Okay, so one of them basically does the following. It says my distance between my loss between two likelihood functions is simply the following. So let me explain it to you. Okay. So what is this? So let me give you examples. So this is a loss function which is based on a function psi. Okay. So let me just explain to you, how examples of this. So suppose I take loss, this psi function as the identity function. Psi of x is equal to x. In that case, what does this loss function turn out to be? So it turns out to be p comma p star is simply the norm of expectation of x under the distribution p x minus expectation. So basically under the distribution p star y. Okay. For example, if p star is a Bernoulli distribution with probability of heads equal to say 0.9, and p hat p is basically Bernoulli distribution again, but with probability of heads is equal to 0.1, then what does this formula simply evaluate to? Everybody recalls Bernoulli random variable, right? What values does the Bernoulli random variable take?
0 or 1.
0 or 1. So what is expectation of x if the distribution is p?
P itself, if that is the probability of 1.
Yes, so it's 0.1, right? And what is expectation of y if it is p star? Y is distributed as p star?
0.9.
0.9, right? So what is this difference in this case? So in this case, what is the loss evaluate to? 0.8. Okay. So you are understanding how this is computed? Okay, so let me give you another example. So suppose my phi of x is x square. Now in that case, suppose I take the same distributions p and p star, right? Now what will this distance be? It will be, again, norm will be a modulus, and this is with respect to p x square, right? That's the function, because psi x is x square, minus expectation with respect to p star, right, y square. Y is distributed as p star. So who will tell me the answer for this? So first who will tell me what is expectation of x square if x is distributed as p, the same p? Anybody online?
Yes, 0.1.
0.21. How did you get that number?
No, I said 0.1.
0.1. Yeah, it's 0.1 again because it's simply x square times probability of 1. That is 1 square 0.1 plus 0 square 0.1, 0.9. So it's 0.1, right? Okay, what is this value?
0.9.
Right. So what is this loss again?
0.8.
0.8, right? Okay, let's take some other distribution. So let's say P star is Gaussian. Okay, normal distributed. So let's use this notation, normal distribution with mean as 1 and variance as 1, say. And P is again Gaussian, say. And you don't need to take Gaussian again, but just for your mean is say 0 and variance is half, say, or 4. Okay. Now, who will tell me what is, and let's take the function. So let's take both cases. So the first loss is where I use psi x is equal to x. So let us repeat this. Suppose psi x function was x. So here I am presenting a loss, one loss function for each psi function. Okay. So if my psi function was x square, I will get one loss function. If it is x, I will get another x. You can take any psi function. Okay. Okay. So if we take this, what is expectation of psi of x? It is in this case x, right? Where x is distributed as p. So what is this in this case?
0.
0. Okay. And what is expectation of p star in this case?
1.
1, right? And so what is the loss function? It is what? 1, right? Okay. Now let's take the other loss function induced by x square function. So for that I have to compute what is x square. But what is this x square? Expectation of x square when distribution is p? Hello. So what is given here? Variance, right? What is variance? 4. And you already know the mean is 0. So what is expectation of x square in this case? What is variance formula? It is this,
Expectation
right?
of x square minus expectation of x square.
So very good. So what is this? What is this in this case?
It would be 4 equal to 1 minus expectation. So,
4 plus 0, right? What is 4 plus 0? 4. Yes? Yes, no, what is the
Yes, sir.
yes, sir.
very simple things, right? Why are you taking time? So this is expectation of x square minus expectation of x whole square. So what is expectation of x square? It is simply variance plus expectation of x whole square. That is 4 plus 0, 4. Right? Okay. Now what is this? Now what is this in this case?
2.
2. Good. Okay. So what is the loss? What is the loss?
2.
2. Good. Right? So you are seeing that this function of course matters depending on the psi function. I'll get various loss functions. I just gave you examples, right? So is this loss function clear to you? So this loss function has many names based on which kind of um, area you come from. So this so okay, instead of giving lots of names, let me give you a name for the final methodology. Okay, so let's not give names for this. Okay, there are too many names for this, so many that you'll get confused. So let me not name this. So in simple words, you can just say mean matching distance. Let's call it. It's not a, it need not be a distance. Mean matching loss. Okay. So which mean it is mean of psi of x. That's what it matches, right? So what is it intuitively doing? It's simply matching the expected value of this function psi. And psi has a name. People, I mean, okay, let me not give, again, let me not confuse you with names. Okay. So let me give you another loss function. Here's another way of computing the loss function. It is given by the expected value of the following function: p star x by p of x. Okay. So this is called as KL divergence. There's no big confusion in names here. So let me name this. So this is called KL divergence. Okay. Now let me give you examples. So let's take again the same examples as previous case, right? Okay, so let me mark everything with this with another color. So what will be the KL divergence loss for these two? So it will be expectation under the Bernoulli distribution, the first P star Bernoulli distribution of log of P star of x and P of x, right? So let us simply write this down. So P star is first of all a discrete random variable. So the formula for expectation is the value the random variable takes, that is log of P star of what are the random values the random variable takes? 1 and 0, right? So P star of 1 by P of 1 into probability of 1. What is probability of 1 in this case? P star of 1. In this example, what is P star of 1?
0.9.
0.9.
0.9, right. So 0.9 plus log P star of 0 by P of 0 into 0.1, right? So let us simplify this further. This is log of, what is P star of 1 again? It is 0.9 by, what is P of 1? P of 1 is 0.1, right, times 0.9 plus 0.1 times log P of 0. P star of 0 is how much? 0.1 by 0.9, right? So what does it simplify to? Some 0.8 times log 9, right? Yes? Yes or no?
Yes.
Okay. So what was the previous loss function we got? 0.8. So this is not very different. There is a factor of log 9. That's all. Okay. So many of these loss functions are related. It's not that they'll give arbitrary values. Many times they'll give related values. What are the exact relations depend on the psi function and the distributions in question. So but they won't be so apart from some properties which are not directly related to the value of the loss, there'll be no much difference. So let's just for For another example, let's try to compute for KL divergence between these two. Okay.
Sir, we
So what is
can't
the,
see your screen. I
is
can't
it?
see at least. Yeah.
So everybody else is able to see?
No, sir.
No, sir.
Okay. Now?
Yes, sir.
Yes, sir.
Okay. So I'm saying let's try to compute the KL divergence loss for this example, Gaussian example, right? In that case, what is the loss function? Let's just write it down. It will be expectation, but what kind of a random variable is P star? Gaussian, right? So it's continuous. So I have to do an integration of log of the density value at x by density value at x into p star x dx. This is what I have to compute, right? Okay, now this is a complicated thing, right? So this will be basically what? Log of e to the power of, so what is the density function for p star? It is 0, it is 1 1, right? So 1 1, so it is minus half x minus 1 square by 2 sigma square, which sigma is 1, sigma square is 1. So by root 2 pi sigma square, which is 1, by e to the power of minus half x minus 0 square by, what is sigma square in this case? 8. 4, right? So 4 2s are 8. So I get an 8 by root 2 pi sigma square, which is a 2 factor, which comes, right? So, okay. So root 2 pi gets cancelled anyway. So I have a 2 factor remaining. So by 2, which will go in the, okay, so that's okay. And I can also simplify the e to the power of term. We will do that, but it is p star of, this p star of x, and p star of x also I know, but let's not substitute it. Okay, now this simplifies to what? Log 2 times p star of x integral, because log a into log b is log a plus log b, plus integral of log of e to the power of something. So it basically is 1 by 8 x square minus x minus 1 square by 2 p of x dx, right? Okay, so everybody is with me, or somebody is lost? So simplifications are fine, right? Please let me know if I missed a half division or minus
Sir,
sign some.
that 2
Yeah,
and sigma square both are in the denominator, right? It's 2 and 4 square.
2 and
That you made it into 8, but it was 1 by 2 and sigma
1
square,
by
which is,
2 sigma square was 4, right? Sigma
yeah,
square is
but,
also in the denominator.
oh,
So
okay.
it's 1 by
Sigma
2
square
sigma
is
square.
4. Okay. Got it.
Right. So what is integral? What is this integral? Anybody?
One by p star of x.
Log 2 is a constant. You can bring it
Oh,
out.
okay.
So what is integral p star? Okay. What is integral of the density function?
1.
1.
So what is taking so much time? So it's log 2, right? So this is log 2 plus integral. Now we know the funda. We just need to, collect terms of x square. So what are the terms containing x square? So it's x square by 8 minus x square by 2. So it's minus x square. What is the expression? Into 3 by 8, right?
Yes,
Yes.
sir.
No. 3 by 8, right? So 3x square by 8. So basically it is the first quadratic term will be simply 3 by 8 times expectation of x square, where x square is Gaussian distributed with p star, right? And then what will be the term which is linear? Linear term will be plus 2x by 2, which is x, right? So plus expectation of x, right? And so then
Yes.
there will be minus 1 by 2, right? And integral of density is 1. So I'll just simply get minus half, right? Okay. So what is this for? Now, irrespective of whether, okay, so let's go slow. So what will be this expression be? What is p star minus 3 by 8 into what is expectation of x square when p star definition is here, right? What is expectation of x square? 4. No, 2, right? That's what we already used. So 2 plus 1 minus half. That's equal to 1 by 4. So this is 3 by 4. So 1 by 4 minus half, which is 1 by 4. So log 2 plus 1 by 4, right? Everybody got the same answer? 1 by 8, right? Oh no, or half minus. So 1 by 4. Yeah. So everybody got the same answer? So let's see what was the answer we got earlier. Earlier we got 1 and 2 as the loss functions. Now we are getting some number. Log 2 will be some number less than 1. So almost 1 plus 0.25. So this is a number almost, little greater than 1. So it's between these two loss functions, right? So again, this is not very different in terms of the loss values. So it makes sense, right? Okay. So I think these are enough examples, right? So I gave you 2 sets of distributions and 3 loss functions. So okay, so let's come back to our original problem. So is the discussion on loss functions for likelihood functions clear? Yes, no?
Yes, sir.
Okay. So now what we have is we want to solve this problem, minimize P loss of P and P star. Okay, till there we are there, and we have 2 cases. So let's explore each of this case separately. One is we want to find this of x minus, this is under P, minus under P star phi of x. This is one case. The other case also has an expectation, right? So expectation under P star of P star of x log of by P of x, right? Okay. Now what was the case in case of ERM? In case of ERM, what was the problem we had? We wanted to minimize G. There was also an expectation again with respect to P star loss of G of x comma y. Okay. So fine. Is this fine? So shall I proceed?
Yes, sir.
Okay. Now let's look at which of these terms are known, which are not known. Okay. Now this term is known if P is known. P is my variable. So this term can be computed at each P. So this term does not create a problem. The blue term does not create a problem. But this term, is that term known? No, because P star is not known. So this term is not known. So in my entire optimization problem, there is only one unknown term, which is expectation of P star, expectation of P star of something, right? Now that's analogous to this case, right? In case of ERM also we had expectation under P star, and we know how to handle it, right? How did we handle it in case of ERM? How did we cancel? How did we handle?
Lost.
Uh, I didn't hear.
Average
Sample
loss.
Average. We substituted by the average. So that can be done again here also. So let's do that trick. So this can be approximated by what? Minimize with respect to P, expectation of P psi of x minus 1 by m. So what is the sample version of this expectation? It is simply 1 by m, I equal to 1 to m psi of xi, right? So everybody is clear with this step? So I just replace this expectation by the average.
Hello.
Hello, sir.
Hello.
Hello?
Hello.
Yes, sir.
Yeah, I seem to have lost the connection. So let me repeat. So are you able to see my screen?
Yes, sir.
Yes, sir.
So I was just saying, so now we have this, so let me repeat the, so this is the problem we have to solve, right? Everybody is clear with this problem? If you use the first loss function, this is the problem we have to solve, yes?
Yes, sir.
Okay. Now, in this problem, this expectation simply depends on my variable. So for each value of my variable, I can always compute this. There's no problem. But the other expectation, that can never be computed. Why?
Because it represents a true population, which we
Because P star is unknown. The underlying distribution is unknown, right? So the only unknown in this optimization problem is this term, right? Expectation of some function under P star. But such a function you also had in case of ERM, right? In case of ERM also, my objective was expectation under the unknown distribution, right? So in that case, how did we solve the problem? What was the first step? We approximated the expectation by the average value. So in this case, what is the obvious thing to do? We will also approximate the expectation by the average, right? So 1 by m. So So everybody is clear with this optimization problem? How do you solve it? We'll come to it later, but is the problem clear?
Yes, sir.
Yes, sir.
So this is very similar to empirical risk minimization, right? So this is what it is. So it is very similar to empirical risk minimization, but without any bias. Correct? Because we didn't put any restriction like this. Now, in case of ERM, without bias, there was a failure. This failed, right? Why did this fail? Because there were many trivial solutions, and some of these trivial solutions may achieve very, very bad true risk, right? Now, let's see if such a thing happens. So, we expect this algorithm to fail. This should also fail. But let's see why does it fail, or if it fails or not, right? So my claim is that again this problem has trivial solutions and it fails. In fact, it has only one trivial solution. There is only one solution and that solution is trivial and that solution is useless. So can anybody tell me what is the solution for this optimization problem?
Again, a distribution which has exactly same values as the
Right.
sample
Very
distribution.
good. Okay, very good. As this sample distribution basically, right? So you take a distribution such that P of psi of xi is equal to 1 by m for all I. So it's a uniform distribution over psi x1, psi x2 to psi xm. That's all. So at any other new point, what is the value of the likelihood? 0. Only at these points there is a mass and it's in fact equal. Okay. So with such a probability function, likelihood function, what is expectation of P of psi of x? You know the answer, but it is again the same thing, right? So that's why this value is 0. You know, so because with this choice, so with this choice of likelihood, the value of this objective is 0. Okay, and 0 is the least value you can get for this objective, right? Why? Why is 0 the least value you can get for this objective?
An absolute difference.
Because it's a norm. So norms are always greater than or equal to 0. So I already showed you one distribution, which is a uniform distribution over these, mapped training inputs, where this value of the objective is exactly 0. That means I have solved this problem. This is an optimal solution.
So one question. So if the sample given has multiple samples for the same value of x, then it would be
Right.
like 2 by m
Then
or
it will be
something
2
like
by
that.
m. Correct. But still it's a useless distribution. Why is this distribution useless? Because the whole goal of machine learning is for new inputs or unseen inputs. Also, you should be able to generalize well, right? So what will be the expected? So if you go back with this, answer and solve this problem, and ask what is the true risk will be very high because the probabilities itself are very low for any other point, right? Okay. So, so is this clear that this is a very, very bad solution? It's trivial, but it's a bad solution. It's like learning nothing, right? I'm not generalizing to any new point, right? Okay. Now, you can also show that this is the only solution. There are no other solutions. Anyway, so but this is fine, right? Why is this fine? Because even in case of ERM, without bias, there was a failure. So what was the idea in case of ERM? We introduced a restriction, right? We introduced a bias, inductive bias. So now what will we introduce? We will also introduce a bias, but now the bias will be on likelihood functions. So it's a probabilistic bias, probabilistic model. You will introduce a restriction on the probabilistic, the likelihood functions that can be taken, right? So that's the next step. So this is the equivalent step. So instead of minimizing over all likelihoods, you will now minimize over some likelihood functions in capital P such that, or capital M, okay, such that your expectation under P of psi of x will be close by to 1 by m equal to 1 to m psi of x. Okay. So this is equivalent to what? This is equivalent to empirical risk minimization with inductive bias. Now you may not call it inductive bias in this case because it's not the functions g which you are biasing on. It's their likelihood functions which you are having a bias on. So usually this set is itself called as the probabilistic model. That's the rough terminology. So people call this itself as the probabilistic model. Now, what were examples of inductive bias? Linear functions, quadratic functions, so on and so on, so on and so forth, right? So we called linear inductive bias, so on and so forth. So what will be names of these models? Again, similarly, you will take a model containing all Bernoulli likelihoods, then it's called the Bernoulli model. Or you will take all likelihoods that are say Gaussian, then it will be called Gaussian model. Okay, so on and so forth. Okay. Okay. So the question will be of all Gaussian model. For example, if you take Gaussian model for all Gaussian likelihoods, which is the Gaussian likelihood which achieves the same expectation of this phi function that is equal to the average value of the psi function of the triangle. That's the question you will ask. And whatever is the answer for that, you will declare it as the answer, right? So is that clear? So if you do this problem, so it's called so if you solve this problem, right, many a time actually you will be able to solve this problem with zero optimal value. So actually the problem that has to be solved is expectation of psi of x is equal to 1 by m. So instead of calling it a optimization problem, it's actually a problem of solving some set of equations. So if you solve this method is called as method of moments. So this method for estimating the underlying distribution is called as method of moments. Okay, so what does it do? It simply tries to match the values of the moments with the empirical value of the moment. That's all. Okay, so is method of moments clear to everybody? But when it does this match for moments, it does not search across all probability distributions, but only those in a particular model, okay, which is selected a priori, right? That's the. Otherwise, if you don't search in a particular model, you may not get any sensible answers. Okay, so is everybody clear with method of moments first?
Sir, can you repeat the that failure part, bad solution again? Like,
Bad solution. Okay, so did you understand why this is a solution?
no, sir.
No, so suppose, I mean, okay, let me, suppose somebody gives you this distribution. What is this distribution? Whenever, whenever the random variable psi of xi takes the value psi of x1, say, that probability is 1 by m. And similarly for every I, for all I. That's this distribution.
Uniform, you mean?
Uniform over these. Okay, so psi of x distribution is uniform over these values. That's all I'm saying, right?
Okay.
Did you first of all understand the?
Yes.
Okay, right. Now why, now the question is, why is this a solution, right? So to understand why is this a solution, let's first compute what is the value of expectation of psi of x with this distribution? What is the value of psi of x? Psi of x, is it discrete or continuous? It is discrete distribution. It's uniform in fact. So its value will be a summation over all values of the variable. What are all the values of variable? For each I, psi of xi are the values into probability of psi of xi, which is 1 by m. So what is the answer? Simply 1 by m summation of these. Is that clear?
Yes.
Okay.
Yes, sir.
So with this particular distribution, what is the value of this objective function?
Zero.
0, right?
0.
Okay. So I am now presenting one likelihood where the objective is 0. But what is the least value of the objective ever?
0.
Zero.
So what should be this? Shouldn't this distribution be the optimal?
Yes.
Yes, sir.
Okay. The only thing, that's all I'm saying. So the only thing which is perhaps you have to go home and show or try if you are interested is this is the only solution. There are no other solutions. Okay. This
Okay.
is definitely a solution, but there are no other solutions also. That also you can show. Okay. Okay. Now all this is about why this is a solution. Now, why is it a bad solution? It's a bad solution because whenever you are estimating a distribution, what is it doing? So you are given these samples, right? Xi, Yi, Xm, Ym. So what is this distribution doing? It's simply giving 1 by m weight to everybody. That's all. And what will be its answer if I give a new sample? Some, x dash, y dash, what will be this value? This will be
1 by
0.
m.
0. That means it will simply say, I just, these don't come from a distribution. So if you start with a distribution which says the entire world for me is only these samples, then how good will be this distribution?
Yeah.
It will be very bad, right?
Yes, sir.
It's useless for the purpose of machine learning. Is that clear? Now this is what I'm calling as bad solution.
Yes, sir. Got
So
it.
whoever asked the question, did you understand clearly or still I can explain in other words if you
No, I got it, sir. Thank you.
got it, right? Okay. So any other questions, please? Okay. So what we'll now do is we'll give some examples of models like Bernoulli, Gaussian, and we'll see what method of moments gives us the answer that we will do. But before that, let us also discuss what happens if you start with this loss, the KL divergence loss, right? Now that loss also, what's the story? That loss, here is the story. The story is as follows. There is one expectation involving the unknown distribution that can be approximated, but still there is this P star inside, right? That was never appearing in other objectives, right? So nowhere, if you recall, here for example, nowhere P star is appearing outside the expectation. Here also P star was never appearing outside the expectation. So there was no problem. But in this case, there is P star appearing again inside. So is there a way to remove it? If this was not there, then I can solve the problem along the lines we did earlier. So do you think you guys can eliminate this?
You can write log P star by P as a log P star minus log P.
Very good. So just use the properties of log. Log A by B is log A minus log A minus log B. And expectation is a linear operator. So expectation of A minus B is expectation of A minus expectation of B. Right? Now, what is this term? So we have to minimize this term with respect to P. But this term, blue term, is a constant, right? It does not depend on my variable. So I can ignore it for the purposes of optimization. So it does not matter what that value is, right? So the problem which I have to actually solve is what? minimize with respect to P minus expectation of P star, expectation under P star of log of P of X. Okay. But isn't this same as maximizing the expectation? Minimizing minus expectation is same as maximizing the, right? Minimizing a function is same as maximizing the negative of the function, right? Okay. Now look at this problem. This problem has P star at only one place. Again, in an expectation. So what is your usual idea? Like in ERM, you will simply approximate. So this is like you will approximate this by this quantity. Okay. And again this will fail. Why? Because this is like ERM without any bias. Right? So we know such things fail. So we'll see why this fails. You have to tell me why this fails. So go home and do this as homework. So you have to tell me why this fails. Okay. So let us not spend time on that in the lecture. So again here you can give the reason is you will get a trivial answer, and that trivial answer will be very, very useless in terms of machine learning purposes. Okay. So what will you do? You will introduce a bias. You will say I'll only search within a model. I'll not search within all possible models, and I'll search for those that maximize this log, sum of the log of the likelihoods. Okay. Okay. Now you can also simplify this further. What is summation of logs? It is log of the product, right? So I can write this as 1 by m log product of, here my curly pi is notation for product. Okay. Now, whether I maximize log of some function or the function itself, it is the same because log is a monotonic function. So this is also same as maximizing these product of likelihoods. But what do I know about the samples xi? They are all IID samples. So what is the product of the individual likelihoods of the samples? It is same as the likelihood of the entire data, right? So this is hence called maximum likelihood estimation. Maximum likelihood estimation. Okay. It's popularly called as MLE. Okay. Okay. So any doubts in MLE derivation? Very simple, right?
Sir, just can you scroll up?
Yeah.
So you mentioned one of it is a constant. So how when you remove that?
Right.
So I did not get why it's a constant, sir.
So does this depend on my variable P?
No.
No. So it's like, so this is similar to, you want to minimize with respect to x, 3x plus 4. Isn't it same as minimizing 3x?
Yes, sir. Okay.
That's all I'm saying.
Yeah.
You can ignore 4.
Okay.
So this is like 4. Okay, constant. And that is good because that constant in this case is happens to be unknown. So why do you want to deal with it? Ignore it. Okay. So is this clear?
Yeah.
So any other doubts, please? So, so to summarize, now we have 3 methods. One method is what? Empirical risk minimization with inductive bias, which looks like this. So I'm writing all these things in a bigger font. That's all, so that you can stare at them individually. Okay, GIXI. This is what? ERM. This is non-probabilistic modeling. ERM with inductive bias. Okay. Then there is generative or discriminative, basically probabilistic modeling. In either case, you will have to solve this problem, which is of estimating a distribution given the samples, for which you will have to either solve, you have to find a likelihood in a set of likelihoods that matches moments in this sense, okay, or the other possibility is you have to find a distribution in a set of models again. So all right, which maximizes the likelihood of the entire training set, right? So the common thing first of all is always there is this bias. So without the bias, nothing works. That is the first thing to observe. Second thing to observe is all these quantities are empirical estimates. This or in fact this. This is also an empirical estimate. Why? This is in fact a version of this. Right? So all these are empirical values. The good thing is they can be computed because they are available. The bad thing is they are only approximations, right? But the hope is that if you take nice models, either probabilistic or nice inductive bias, then nice fellows such that the estimation error is low. That means the models are not too complex, and also the modeling error is not high. That means what? In case of inductive bias, what is the meaning modeling error is 0? It means G star belongs to G. Here in this case, what is modeling error 0? This happens if P star belongs to M, then modeling error will be 0. Right? That's what is the implication here. Right? Okay. Now in either case, if you take larger and larger M's or G's, they will have, then worse is the estimation error. That is true. So again, you want to deal with simpler models, that give you good training set accuracy. Okay. So if this entire story is fine with you, so let's take a break and then let me give you various examples of probabilistic models and how method of moments and what estimates do method of moments and maximum likelihood estimate give. So I'll give a lot of examples and we'll apply it to generative modeling and actually give examples of classifiers and regressors. Okay. So that's what will come in the next part of the lecture. So shall we take a break? Are there any questions?
Sorry, from the minimization formula, how did you come up with the method of moments?
Okay, so that's just because most of the time, see, like in this case, most of the times the models we deal with are rich enough that, so let me, this is not expanding. Oh, okay. See, most of the time what will happen is our models are rich enough such that this equalities itself has a solution. Now, if this has solution, I don't need to solve this optimization problem, right? Because I already know what is the optimal value of this, optimization problem. It is 0 because already I can find a solution for an exact match. So why should I look for any other match? Correct? So this is
Yes.
exact match, right?
Yeah.
This is for looking for a nearby match. So let me put colors. Maybe it's not. Okay. So the green fellow is looking for a nearby match. Yes or no?
Yes, sir.
It's looking for a close by value of these distances, right?
Yeah.
Whereas this pink fellow, what is it looking for? It's looking for an exact match. Now, suppose I tell you that my models have rich enough, distribution such that I can always get a match for any data, say, 100 points or 200 points, 1000 points, whatever it is, I can always get a match, say. Then what will be this solution? This solution will be the solution of matching, right? That's very clear, right? So instead of solving this problem, people usually, say, let me actually find for an exact match. So I'm not saying always exact match is possible. I'm not saying that. But for most models, exact match is possible. For at least the models which we will study, we'll always carefully choose a psi function such that I can get an exact match. Now you can always debate whether exact match is better or a close by match is better and carefully do some modeling. But most of the time that is not worth spending time on. So people usually go with this solution because it has other relationships. We'll shortly see that method of moments will give you the same solution as maximum likelihood for proper choices of the function psi. Okay, so that's why people prefer to solve these things. So did I answer your question?
Yes, sir.
So I'm not saying that they are equivalent, but they are definitely equivalent if this equality holds. Because if this equality holds, this norm is 0, which is the least value the objective can take. Right? So I'm saying most of the time people assume that the model has enough distributions that they can do an exact match. In which case they are anyway solving this problem, this optimization problem. And if not also, they'll only miss by, so they'll only, okay, so they'll take an appropriate psi function, that's all. Okay, any other questions please? See, these things will be more clear when I give you examples. Okay, so so any other questions please? Okay, so we'll meet exactly at 3:40 and resume the lecture. So shall we resume? Hello. Hello.
Yes, sir.
Okay. So now what we will do is we'll give some examples of probabilistic models like the Bernoulli model, Gaussian model, very simple models, and try to see what answers will the method of moments or maximum likelihood estimation give. Okay, and further we will later on use it in solving the regression problem or the classification problem. Okay, so to summarize, here's what is the problem and the solution. So the problem is there is some unknown distribution and you are given some IID samples from it, right? M samples. Okay. Then what you will do is the following. You will first, based on the nature of P star, you will assume a model. Assume a model, probabilistic model, such that P star is belongs to M. Okay. For example, in a particular application, you may have the background knowledge that the underlying distribution is a multivariate Gaussian distribution. Okay. Then you will take your model as set of all Gaussian functions, Gaussian likelihoods. Okay, and such a set is called as the Gaussian model. Okay, similarly, in some other application, you may have the background knowledge that the underlying distribution is a multi-nodal distribution or something like that, right? So you may have various things known. Based on that, you will decide what is the set of all likelihoods you will search within. Okay. Now, obviously, if P star is not guaranteed to be in your model, then there will be modeling error. Okay, so let's for the time being assume that there is no modeling error. Okay, okay. So this is the first step, step A, where you should first choose a model. Okay, then what will you do? What is the next step? Model will typically be a set of likelihood functions. For example, in case of Gaussian, uh, how do two Gaussians differ by the mean and the variance, right? So if you change the mean and the variance, you will get different likelihood functions, right? So these things are called as, these values are called as parameters, okay, of the model. Okay. So remember, in case of linear model, what was the parameter? W, right? Which went into the formula W transpose X, right? So now what are the parameters? The parameters of the likelihood function which are in your set of likelihoods, right? Okay. For example, parameters are like mean and the variance and so on and so forth. Okay. So parameters in general, let's call it as theta. Okay. Okay, so the second step is you will try to find the right distribution, the correct likelihood function based on the data, right? Now you have two ways to, and the problem of finding the correct likelihood is same as the problem of finding the correct parameter, right? So for models which are nicely parameterized, the problem of selecting a likelihood is same as the problem of selecting the right value of the parameters, right? So this step is called as, so the first step is the probabilistic model, choosing the probabilistic model. The second step is called as parameter estimation, right? Now there are two ways we saw in which parameter estimation can be done. One way is method of moments. The other way is maximum likelihood estimation, right? So in method of moments, what do? You further choose a function psi and then match, find that theta with which the likelihood of the expectation of psi of x will match the average value of the psi function over the training set. So this is what you do in case of method of moments. Now instead of saying here the unknown p, I am putting the parameter, because if the parameter is known, the distribution, the likelihood function is known. Okay, so that's the only difference. Now in case of maximum likelihood, what will you do? You will again, depending on the model, there will be a set of valid values which the parameters take. So let me call that as capital theta. For example, in this case, the means can be any real number, but sigma square will always be strictly greater than 0, right? So r cross r plus is perhaps what we will call as capital theta, okay, in this case. So those are nothing but the set of all possible allowed values for the parameters, that's all. Okay. So in case of MLE, what will you do? You will search for the likelihood function that maximizes the entire likelihood of the training set. Okay. Okay. So once you find the right parameters, so say theta hat, then what will you do? then the answer is basically the likelihood function at theta hat. That's what is the answer we are seeking. So this will be the approximation for P star. Okay. Now we'll go back and use this in generative or discriminative modeling. Okay. Now let's give some examples of models. Okay. So let's start with what is called as the Bernoulli model. Okay. So this is a very simple model. It is nothing but the set of all Bernoulli likelihood functions. Okay. Yeah. So what is special about Bernoulli likelihoods? First of all, the random variable takes only two values, 1 and 0, right? And then the probability of the likelihood of 1 is the parameter. Let us call it as theta. So that's like the probability of heads, right? If we are doing a coin toss experiment, right? So that's the parameter. And what are the allowed values for the parameter? It should be a value between 0 and 1, right? So given any value of theta, you will retrieve a particular Bernoulli distribution, right? And with various values of thetas, I'll get various Bernoulli distributions, right? So that set of all Bernoulli distributions is what is called as the Bernoulli model, and it's parameterized by this value of theta. Okay. So is the Bernoulli model clear to everybody?
Yes, sir.
Okay. So for example, if I have to write a general formula for likelihood function at x, what are the valid values of x? Again, 0 and 1. So can anybody tell me a nice formula for the likelihood involving theta, of course? So what is the likelihood of x when the probability of 1 is theta?
Theta.
Always theta for any x?
No. So
My
when x
answer
is
is
equal to 1, then it is theta. If x is equal to
right.
1.
So if x is equal to 1, then it is theta. Otherwise, it is 1 minus theta. Yes? Everybody agrees with me?
Yes, sir.
Yes.
So this also can be written in nice form, right? So
Theta into x.
right. So this is This is how people write it. So this is also correct, right?
Yes, sir.
Okay, so okay, now let's try and see what does maximum likelihood estimate gives for this model. Okay, so for solve, so basically what is the problem you have to solve? The problem you have to solve is maximize theta belongs to, what is the range of allowed values of theta here?
0 to 1.
0 to 1. Good. And what is the objective? Objective is the product of likelihoods of each of my, that's what is the the likelihood of the entire training set, right? So which is equal to what in this case? So 0 comma 1 into theta to the power of xi, product of into 1 minus theta to the power of 1 minus xi. But suppose I tell you that the number of times 1 occurs in the data set is m1 and the number of times 0 occurs in the data set is m0 and the total number of points in my data set are m. Can you rewrite this optimization problem in terms of m1 m dot?
So it'll become like a binomial distribution, right?
Yeah, tell me what is the, so see, when the only thing is that whenever xi is 1, all those theta will get multiplied, but how many times it will be 1?
M1 times.
Theta.
So theta to the power of m1 into 1 minus theta, how, when will it occur? Whenever xi is 0, right? And how many times is that? M naught, right? So is this clear to everybody?
Yes, sir.
Okay. Now, how will you solve this problem, right? Now, for any function, if we want to optimize, the first thing we will do is look at its critical values, right? For example, the function could be, some function like this, right? So you look for basically those values where the slope is 0. They are called as critical points, right? Agreed? So these are called as critical points, right? Or stationary points. Everybody recalls this thing?
Yes.
Yes, no? So these are called as stationary points, the points where the first order derivative is 0, right? Okay, so let's look at the critical points of this function. So when is the slope 0 for this function? So it is simply m1 theta m1 minus 1 times 1 minus theta m naught. I'm using by parts formula. Then this into m naught into 1 minus theta to the power of m naught minus 1 into minus 1 for the derivative of minus theta, right? Okay, so this should be 0, right? So if I cancel out common terms, what will I get? I'll get m1 by m naught is equal to what? Theta by 1 minus theta. Yes. So if I cancel out terms, this is what I'll get, right? So this will get cancelled with this, theta will remain. This will get cancelled with this, only 1 minus theta will remain. So if I rearrange, this is what I'll get, right? Okay, from this, what is theta? m1 by m, right? Okay, now let's see these. So what does it say? This is the only critical value. That means the graph actually looks like this or like this or is constant. Constant is not possible because the only, so these are the only possibilities, right? Right? In which case does it represent a maximum? When the double derivative is
Less than 0.
Less than
right.
0.
So go home and check that whether the double derivative is greater than 0 or less than 0. And the other thing you need to check is, thankfully our critical point always satisfies these constraints, right? So if the critical point, suppose I am looking at this critical point, but my actual constraints are saying that my variable should lie here, then there is a problem, right? This will not be a solution. This won't be a solution. But thankfully in our case, this is always a number between 0 and 1. So it will be a solution, right? So go home and check the sign of the double derivative. That's the only thing you have to do. So if you check that, then this should be, this is the only local maximum. So it should be the global maximum. Okay. So what is the MLE solution for Bernoulli model? The answer is simply the fraction of number of ones. Is it the usual way you estimate the parameter? Yes, right? So MLE is nothing different from the usual estimate for probability of hits. So is that clear?
Yes, sir. But only thing is
Ah.
that continuous function graph you got max and
Mhm.
minima. How did you got
Mhm.
these two graphs? Like,
So because my critical point, there is only one point where slope is 0. So when will slope be 0 at only one point? Either the graph should look like this or this. Because if it turns further, slope will again be 0. So that is not possible.
okay.
Okay. So here the derivation shows there is only one point where slope is 0, right? Which is m1 by m.
Okay, sir. Got it.
Okay. So you have to confirm that it is indeed this case, not this case. And also nicely our region of lies here. It's a point in between 0 1, so it will be a valid solution.
So that we can say based on whether it's a maxima or a minima, right?
No, irrespective of whether it's maxima or minima, suppose your critical point is outside the domain of interest. So here the constraints are 0 1. Suppose it so happens that this value of slope is 0 at some point m1, which need not be a number between 0 and 1. Then there is a problem.
Right. Right.
Right? Then you can't say m1 is the answer because m1 can never be the answer. It's not even a value between 0 and 1. Correct? So that those cases you should be careful. But luckily in this case, it's already a number between 0 and 1. So it's a solution. Okay. So is that fine?
Yes.
Okay. Any other doubts, please? Okay. Now, in case of Bernoulli model, suppose I ask you the following. Suppose we want to deal with method of moments. Method of moments, if you want to apply, there is one decision you want to make, right? What is the decision? What is the psi function? Hmm? So can somebody tell me what is the psi function with which I'll match the MLE solution? What is my question? Is there a psi function with which if you solve this problem, that is, expectation of psi of x is equal to 1 by m psi xi. Suppose I solve this problem, and my answer with the valid values of theta, which are between 0 and 1, and for the answer for this should be what? Should be same as the MLE solution. That means m1 by m. So do you
So
guys can you guys guess such a psi function?
psi xi is equal to xi. I mean that whatever is the output.
Very good. Very good. So this works in this case, right? So suppose I take psi of x is equal to xi, the identity map. Then what is expectation of theta of x? That's what is this quantity, right? So what is that? That is equal to theta, right? Because it's a Bernoulli variable, and that we should equal to 1 by m sigma xi, right? But what is 1 by m sigma xi? It is simply m1 by m, right? This is the exact match. This is the MLE solution. Okay. So many a time, please remember this, many a time, you know, you can always select a function psi such that you will match the MLE solution. Now, if so, you may ask, why do you need method of moments? Okay. Shortly, I'll introduce you to another model where you cannot, I mean, it is difficult to solve the MLE problem because you need to know optimization literature, right? So you need to know results in optimization to solve optimization problems. Whereas to solve this, perhaps you don't need optimization. Okay, so this may be easier to solve in many cases. So that's why it is important to understand method of moments also. Okay. And I'll also tell you what are intuitive ways of selecting psi. See, I'll give you a hint. So please remember this. Always psi should be such a function so that the expectation of psi of x characterizes the distribution. That means what? If expectation of psi of x matches, then the distributions are same. So such should be psi. In other words, psi should be sufficient to match the distribution. Then what will happen? Because I'm matching this distribution with the underlying distributions, at least the sample version, I'll be correct. So, okay. So most of the time it should be some kind of a sufficient function for characterizing the distribution. So such sufficient functions are called as sufficient statistics. This is not a definition. I'll later on, I mean, if time permits, I'll give a definition. But intuitively, this is the thing, right? So what are sufficient statistics? Those functions such that this happens. E theta of psi of x minus e some other quantity, some other distribution, say p star of psi of y. Y is distributed as p star. Here x is distributed as p theta. So this is 0 if and only if x is equal to, or distribution of x is equal to p theta is equal to p star. Okay. So such size are called as sufficient statistics. Okay. So usually sufficient statistics will be those functions which will retrieve your parameters for the model. For example, in this case, psi of x is equal to x, it retrieved one of the parameter, right, which is theta, right? Okay, so let's see some more examples, then the notion of sufficient statistic will be clear. Okay, let's pick up univariate Gaussian model. Okay, so what's the Gaussian model? The set of all Gaussian likelihood functions. So what is the formula for the likelihood function of Gaussian? It is given by this. Its parameters are theta, where theta is mu and sigma square. Okay, so it is e to the power of minus half. So x minus mu square by 2 sigma square by root 2 pi sigma square. Okay, and this holds for all x belongs to R. And this belongs to R, and this is strictly greater than 0. Okay. So what is the set of allowed parameters? Allowed parameters is R comma R plus plus. Okay. So what are these? So these are called the parameters. So this is another parameterized model. So everybody remembers this formula, right? For Gaussian likelihood density function. Yes, no?
Yes, sir.
If you say no, then it means you didn't study the material I
Yes,
gave
sir.
you.
Yes.
Okay. So, Okay, let's see how to solve this problem using method of moments. Okay. So using method of moments, if you want to solve, somehow what should I match? See, now the idea is very simple, right? So how will you select psi function? Such that you will first of all match mu's and match variances, right? How will you match means, you know, you should take this function to match this. When, how will you match variance? What function of psi should we use?
X square.
X square is enough, or so you should basically use x square x minus expectation of x square, right? That's, but expectation of x has been already matched here, so x square will be enough, right? So your guess is right. So let's take a psi function. So this is how you will imagine constructing psi. All the parameters, how will you match and put them in a vector, right? So suppose I take this psi, right? Then what will if with this psi, what should I match? I should match this part and this part both, right? So that's what will happen. So this is what you have to actually do. X expectation of x and x square should be matched. So basically, let me write it clearly so that, so expectation with respect to x under mu should mu comma theta basically should be 1 by m average value of the xi's. So that's the usual estimates, and this is equal to what in this case? Mu. And what is this expectation of x square? That should be 1 by m xi square. So what does this give you? So this will be sigma square plus mu square, right? So given my data, I can always compute the average value. I can compute average of the squares. Okay. Now given these two, I can always find mu and sigma square from this formula, right? So what will be the formula for sigma square, for example? It will be 1 by m psi square minus 1 by m whole square. And this is the usual, is this the usual formula for sample variance? Anybody remembers the usual formula for sample variance?
X minus mu whole sigma of x minus mu
Right.
whole square by n minus 1.
Right. Right. There are two choices, by m or by m minus 1. So both choices are popular. So is this same as this or no? It is
If you
not,
say
right?
mu is equal to like 0 only then.
Yeah, but mu is not 0 clearly. I mean, this is.
Yeah, you have mu term, so then it is.
So they are not same. That's why, you know, suppose I take another function. This is instead of x minus, say expectation of x, x minus, say 1 by m, you know, x, just to match the, you know, j square. Then what will I get? Then I'll basically have the same thing here. Okay, but in this case, I'll directly have, so what is expectation of psi of x minus 1 by m? Okay, so I should basically have mu here, not mu, the original mu. Then I'll have x minus mu square, right? But what is the expectation of x minus mu square? It's the variance, right? And then what will be this estimate? This will be 1 by m xi minus mu square. And further we will approximate this by 1 by m xi minus this value. If I call this mu hat, then it is mu hat square. So this matches this. Right? So what is the right value of sufficient statistics we should take? It is this x minus mu whole square. Okay. So now I think you got the idea, right? So how will you select sufficient statistics? You will simply select them to retrieve the values of the parameters in many cases. That's all you will. Okay. Okay. So is this clear or any doubts?
Clear, sir.
Okay. So compare this with maximum likelihood. So suppose I want to solve the maximum likelihood estimate. Oh, these are the domain constraints, and then it is 1 by m, so we can ignore 1 by m. So sigma I equal to 1 to m log of p theta xi, right? But what is this for Gaussian? For Gaussian, it is again this I equal to 1 to m, right? So what is Gaussian? This formula? This formula is e to the power of, let me write it again here for your convenience. It's xi minus mu square by 2 sigma square by root 2 pi sigma square, right? So what is log of a by b? It is log a. So log of e to the power of something, that's simply sum of those things. So I can take minus half common, xi minus mu square by sigma square. So sigma also I can take common, 1 by 2 sigma square. And then what will I get? So that is log a minus log b, right? So minus, and this term appears m times. So minus m by 2 log 2 pi square. Fine. So everybody is clear with this? Yes, no?
Yes, sir.
Okay. So now, now how will I solve this problem, right? Now, what is the difficulty in solving this problem? There are multiple variables, right? So it's an optimization problem defined over multiple variables, right? Now, how can I solve this problem? The way to solve this problem is you will solve the optimization problem one variable by one variable, one after the other. Like for example, in case of multiple integral, how will you solve the problem? Suppose you have a multiple integral over three variables, right? How will you solve the problem? You will first integrate with respect to g, integrate the function with respect to x, say, and that will be a function of y and z, and that function of y and z you will integrate with respect to y and z. And how will you again integrate with respect to y and z? Again pick an order, pick say y, and then keep on doing. So everybody remembers multiple integrals, right? Yes, no?
Yes, sir.
Okay. So you remember this, right? You do one variable by one variable, and the order does not matter, right? So first you can integrate with respect to x, or you can integrate with respect to y, and so on and so forth, right? So similarly, in case of optimization problems, you can pick an order of variables. You can pick first to maximize with respect to mu, and then write the maximum as a function of sigma square, like you did here, right? And then maximize with respect to sigma square. Okay. So let's adopt that procedure. So let's try to maximize only with respect to mu the following function, right? So 1 by 2 sigma square, 1 to m xi minus mu whole square, right? And the other term, this term is constant with respect to mu, right? So I can ignore it. Now who will tell me the answer for this problem? So which is the mu value that will solve this optimization problem? Anybody knows?
It is sample mean, right?
Very good. So this we have done already in this course multiple times. So this is same as the least square solution, right? So minimize with respect to xi minus mu whole square. So the answer for this is, what is the point that is closest to a given set of points? Sum of, in terms of the sum of square distances, right? So the answer for this is mu hat will be sigma I xi by m. And that's the same answer which you get otherwise also, right? So MLE gives the same intuitive answer. Whatever this mu hat is, now what should I do? I should solve the problem with respect to the other variable also. So sigma square and 1 by 2 sigma square, and whatever this sum is a constant, right? Because it does not depend on sigma. This entire thing is a constant. Let me call it as C. And minus, m by 2 log, and I can ignore 2 pi also, because log a into log b is log a plus log b. So it's a constant, it does not matter. So for some reason, let me rewrite this problem, as so when you do integration, you do change of variables, right? Sometimes for your convenience, you will say let y be equal to some p square, and then you will do change of variables, right? So similarly, I am doing a change of variables. Okay, instead of calling my variable as sigma square, I am calling my variable as 1 by sigma square. So what are the constraints? Again, y is greater than 0, and here it will be minus c by 2y. That's what will be, so not 2 by 2y, it will be into minus c by cy by 2. So cy by 2 minus plus m by 2 log 1 by sigma square, which is y, right? So everybody understood this change of variables?
Why the plus sign, sir?
Because I have to get log 1 by sigma square, no?
Oh, okay.
Okay. Now what is the problem? The problem is, instead of max, I can do min, and this will be plus and this will become minus. Now check your critical points. Now let's do our critical point business, stationary points. So what are the stationary points for this? C by 2 minus m by 2y should be 0. So that is if and only if y is equal to m by c, right? Yes or no?
Yes, sir.
Okay. Now, how many critical points are there? Only one. Again, good, right? So now some of you may be thinking, why did I do this change of variables? Because of these nice properties. Okay, so go home and don't do this change of variables and try to solve the problem. You will get into difficulties. Okay. Anyway, with that note, let us continue this. So this is the only critical point. So that's good. So there are only two possibilities. The graph is like this or like this. So to confirm, what will you do? You will check the second derivative sign. What is second derivative sign? It is simply this term vanishes, the first term vanishes, the second term is again plus m by 2 y square. Is it greater than 0 or less than 0? It will be greater than 0 for any y, in fact. So how should be the curve? The curve should be like this, right? and this is the point we are looking for. And what is the next thing we have to check? Is this inside my constraint set? Is it inside always? Yes, because C is always greater than 0. Right, that I know. So whatever this is, that should be the answer for 1 by sigma square. So what is sigma square? It is C by M. But what is C? Xi minus mu hat square by M. So is it the same formula you got earlier? Yes. So is it this? This is the same sample variance, right? Okay. So any doubts in the derivations?
I think we'll go through it and then
Okay.
maybe we'll have
Good.
questions.
Sure. So you can please go home and do such derivations. More importantly, ask why questions like why did I do change of variables? Why did I solve mu first? Why did I solve sigma square first? What will happen if I change the order? What will happen if I do some other change of variables? Try all these things. I'm not saying this is the only clever solution, but then you'll understand why some particular choices have been made. Okay. And the other important thing you have to understand is always MLE is giving solutions which are familiar to you in case of these models, simple models. So even in case of other models which are perhaps unknown to you, MLE will give intuitive estimates. That's another thing I want you to note. And and the difference between method of moments and MLE as of now is the following. In MLE, most of the time you can make a nice, clever choice of the sufficient statistics such that you retrieve your parameters very easily. Okay. Whereas in case of maximum likelihood, you will have to do some clever optimization solving, either analytically or numerically. Solving this problem may turn out to be challenging. So sometimes it is convenient to use method of moment because you'll simply estimate the parameters as the empirical versions. That's all. So very simple, you know, uh, way to do the estimation. Um, Whereas in case of maximum likelihood, it may be a challenging task. Okay. Okay. Now later on, when we come to discriminative modeling, we will realize that method of moments cannot even be applied. Okay, so there's no way you can apply method of moments. The only way out will be using maximum likelihood. Okay, so that's why both these methods have their own advantages, disadvantages. One is more general, but it is sometimes complicated. That is maximum likelihood. The other is method of moments, which is simple but very restricted. You can't apply it to all cases. So many times in generative modeling, you will end up using method of moments, whereas in discriminative modeling, you will end up using maximum likelihood. Okay, so that's what happens typically. Okay, so with this note, let me finish this with finish the discussion with some two more models. And in the case of these models, I leave the details to your homework. Okay, and I'll only give the final results. So please go home and verify all the things which I will mention now. Now there are Bernoulli model is usually generalized to what is called as a multinodal model. Okay, a multinodal model is, think about it as a die throwing. Bernoulli is simulates the process of coin tossing, whereas multinodal simply generalizes this notion to the case of die throwing. Okay. Now, so that's the only difference between these two models. So it's the set of all multinodal likelihood functions. So it is parameterized by, so if there are n values, the multinodal takes, right? So x, so say some C1 to Cn, okay. Then there'll be associated n probabilities, right? So theta 1 to theta n, they will all be parameters, but they will all be probabilities. So they all will be greater than 0 and they'll add up to 1. That's the right. So in case of die throwing, this will be the probability of rolling a 1, this will be probability of rolling a 2, and this will be probability of rolling a 6. Right? all these should be numbers greater than 0 and should add up to 1, right? Okay, so in short, so there is a notation we will give. We will say theta should belong to delta n. So what is delta n? Basically this set, the set of all numbers which are in n dimensions but are greater than 0 and add to 1. So that's that figure, that set is called as a simplex. These are just definitions. Okay, so for example, in case of n equal to 2, what is the simplex? What does the simplex reduce to?
Theta belongs to theta 1, theta 2.
Yeah, but how does the simplex look like if n is equal to 2? It looks like a line segment. Yes? Yes, no?
Yes.
Okay. So that is indeed the case, right? In case of n is equal to 2, it retrieves Bernoulli, and in which case, what was theta moving in an interval, right? Interval is a line segment. Remember? So where is the Bernoulli model, yeah, right? So 0 to 1 is an interval, that's a line segment, right? So why did we have only one parameter? Because the other parameters were simply, theta 2 was simply 1 minus theta 1. That's why we didn't take the other parameter. Similarly, in multinolly, you need not take all n parameters. You can always write theta n as 1 minus the others. Okay. Now you can go home and show that the method of moments with appropriate choice of sufficient statistics and MLE both retrieve the following estimate for theta I. Can anybody guess what will be the estimate? If M1 is the number of times XC, if MI is the number of times CI occurs, and M is the total number of points in the data set, then can anybody tell me the guess for formula of theta I according to these estimates?
Mi by n.
That's all. Very simple. Okay. So go home and show this actually. So what is the challenge in case of MM? The challenge is which is the right phi which will retrieve this. In case of MLE, solving the optimization problem. That is the challenge, right? So please do these exercises. They'll be very helpful for you in terms of the exam point of view. Okay. Now there is another model which is the generalization of Gaussian to the n-dimensional case. That's called the multivariate Gaussian. Okay, now this formula for, so this is the set of all likelihood functions which take Gaussian distribution but in n dimensions, right? What do you mean by n dimensions? The output, the values of this random variables will be a n-dimensional vector, not a real number. Okay, so that's what is the generalization. And how does the likelihood function depend on? So this is the form of the likelihood function. It will be e to the power of minus half. Now x is a vector, mind you, so it belongs to Rn. So x minus mu transpose sigma inverse minus mu by 2 pi n by 2 determinant of sigma to the power of half. So this is the formula. This holds for all x in Rn, and mu is any vector. It's called the mean vector. Okay, so it's basically the vector of all expectations. Okay, and then sigma is a positive definite matrix. So did I define positive definite matrices in this course?
Yes.
Positive semi-definite I defined. Positive definite also I defined.
No, I think it was PSD.
Oh, okay. So I'll define shortly. So it's an n by n square matrix which is positive definite, and it's called the covariance matrix. And what is the meaning of these? So if x is the random variable, it takes on values that are in Rn, right? So let me call the first entry as x1, second entry as x2 and xn. Then this ith entry in the mu I will be same as expectation of xi. Okay, that's the definition of the parameter mu. And the ijth entry in the covariance matrix will be simply the covariance of xi and xj. So this is the formula of the covariance. Right. So all these you should have studied some time back, but this is just to refresh your memory. Okay. And what you can show is, as long as x is a valid Gaussian distribution, the covariance matrix will be positive semi-definite. Okay. Now, what is positive semi-definite? Here is the definition. A matrix sigma is positive definite, if it satisfies two properties. If it is a symmetric matrix, and secondly, take any vector of appropriate dimensions and compute this number. This number should be greater than 0 for all x not equal to 0. Okay. If this happens, then you call the matrix positive definite. And if you have to contrast it with positive semi-definite, the only difference is in the second. The first condition remains the same. Second condition is also very similar, but the only difference is this is greater than or equal to 0. That's the only. Okay. So in this case, you can show that covariance matrix is for Gaussian distributions, covariance matrices, this parameter should be positive definite. Okay. And positive definite matrices are invertible. So their determinant is non-zero. So you can divide also, and the inverse is also defined. So this also creates no problem. Okay. So all this is just to recall your memory about Gaussian distributions in n dimensions. Some of you may have seen these figures also, right? So let me try to help you visualize how the distribution will be. So it is difficult to explain from a remote location, but I'll try to do my best. So suppose this is x1, this is x2 axis. I'm talking about n equal to 2 case. Say. So this is a Gaussian distribution which takes on values in R2. Okay. So if it takes on values in R2, in how many dimensions should I plot the density function? Should I plot it in 1 dimension, 2 dimension, 3 dimensions?
3.
3, right? Because 2 for specifying which location I am in, and 1 for the height with z-axis will specify the density value, right? So how will Gaussian look like? It will look like a bell-shaped curve. So imagine a usual 3D bell, okay, sitting centered at this point, say. This is called mu. Okay. So imagine a bell, this is how you will visualize. It's a bell centered at mu, and the bell can have many cross sections, right? So suppose I cut the bell at the tip, highest point, right? What is the density at that point? The highest, right? So that point, if I cut, I'll actually get this point, mu. If I cut it at slightly lower, what will I get? I'll get all points with equal height. That means what? All points with equal density, but lower than the highest, right? So that will trace out this kind of a curve, right? And then the next cut, even lower density will be a bigger curve, bigger circle. And even lower density will be a bigger circle, right? And if you go linearly in terms of height, you will go non-linearly in terms of the radius of the circle. Okay, so that is clear because there is a non-relation. Okay. Now, now mu is clear. Mu is simply a point in Rn. So, and it will be the center of the bell. That visualization is very clear. But if sigma is identity, not identity, if sigma is some square times, some number times identity matrix, then the cross sections will look like circles. Okay. So then if you take a covariance matrix, which is say all threes in the diagonal, rest all zero, then for example, it will look like what? A usual bell with circular cross sections. Or if you take a case where covariance matrix is all twos in the diagonal and rest all zero, then also it will look like a circle cross section. If you take um, a sigma which is like a diagonal matrix, then what will happen is it will look like the cross sections will look like ellipses which are axis parallel. For example, if you may get ellipses, sorry, you can't get, so you will get ellipses like which are axis parallel. So maybe elongated along x1 and compressed along x2. So this is how this is. So my drawing is bad, but these are axis parallel. That means this is one possibility. The other possibility is x2 is elongated and x1 is compressed. Okay. Whatever it is, the principal axis of these ellipses will be axis parallel. Right? They're parallel to the axis. That's what happens when this is diagonal. And when this is a general matrix, when this is general non-diagonal positive semi-definite non-diagonal, then it will be the cross section will be ellipses which need not be axis parallel. For example, you may get such a situation. So you get so these principal axes are not parallel to the original axis. Okay, but in either case you can understand one thing, right? In both these cases, the random variables in each entry will be independent. That's very clear because these are axis parallel, right? In all these cases, the individual random variables x1, x2, they will be independent, right? But in this case, they will not be independent. Okay, that's the other way to understand. Okay, so all this is about the Gaussian model. I hope I have refreshed your memory enough. So shall I give you results about Gaussian model? Everything is clear? Yes, no? Everybody is asleep?
Yes, sir.
Yes,
Yes.
sir. Asleep.
No,
No.
we can continue.
Very boring. Saturday night after lot of work in office, you come back and you teach all these boring stuff.
Yeah, actually, it's the wrong time for this class, sir, because loaded with lot of things. It should be in the morning hour.
Okay. Okay. So I can't help it. You guys registered for the MTech degree. I did not. Okay. So let me just finish this. So what will happen is in this case, so what do you think will be the estimates of this mean vector? That's very simple. The ith entry's estimate will be simply. So I'll give you a visualization instead of all this formulae. So this is how the data will look like in n dimensions. Suppose you have an n dimensional data. Okay. So the first example x1 will, I'll write it as x1, x2, x1n. Okay. So these are what the n features of n attributes or n entries of this vector x1. So let's assume that this is the first sample from my distribution. Okay, the next sample x2 is x21, x22, x2n. Similarly, I sampled m times. What will I get? I'll get m vectors, right? So I'm just writing those vectors. This is the first entry of the mth vector, second entry of the mth vector, nth entry of the mth vector, right? So this is how training data will look like, or not training data, the data will look like for in the estimation problem in case of Gaussian model. So is this clear? Notation, is it clear?
Yes, sir.
Okay. Now, how will you estimate in case of, suppose somebody asks you to estimate the values of the parameters? What are the parameters? It is simply mu and sigma, right? So mu, how many values you have to estimate? N values. Sigma, how many values you have to estimate? N square values, right? So now I'll just tell you how to estimate these things, right? So these are the usual formula which you know, but that will be the same answer in case of method of moments or maximum likelihood. Okay. Now the derivation in case of method of moments is very simple. You will just take the appropriate psi function. But the derivation in case of MLE will be very involved. Because why? The variable will be a matrix which is restricted to be positive semi-definite. So you have to solve an optimization problem in n plus n square dimensions, where the last n square dimensions have a positive definite constraint. So you have to take derivative with respect to a positive definite matrix. So these are going to be very, very technical things, right? So that's why, in case of generative models, you barely use MLE. Most of the times you'll go with method of moments. And once you use method of moments, what will be the estimate for these means and covariances? So let me write it down. So how will you get the ith entry for the mean? Anybody? What should I do in this data table, in this matrix? To get mu I, what should I do? Anybody?
Ith column add
Ith
and
column or ith row? Just to
column.
confuse you. Column, right? Very good. So you should take the ith column. What will that do? It will take each sample's ith entry. And what will you do to get mu I? Simply take an average. Okay. Average of ith column. Very good. Now, how will you get the estimate of sigma ij? Anybody? So how will you guess? You should guess based on the definitions, right? So what are the definitions? The definitions are lying here, right? So okay, this is right. So what is mu I? It is expectation of xi. That's why she gave the formula of average. Now for sigma ij, what should you do? You should take average of these quantities. That's all, right? So who will tell me the answer in terms of the data?
First, you'll have to like matrix wise. If you want to say, if you'll have to create a matrix with the ui repeated across rows, and then subtract from this matrix of all the samples.
Okay. Okay, but you need not do matrix operations. You can tell me intuitively.
Okay, then from
Ah,
each row, sorry, from each
okay.
column you subtract the respective mu, and
No,
then
I just want the ijth entry. Oh, I think you are telling the answer for the entire sigma. I just want the ijth entry. See, if I wanted ith entry of the mean, you just took the ith column and took the average. If I want ijth covariance, what should I do? What does the formula say? I should look at the ith random variable and subtract its mean, and take the jth random variable, subtract its means, and take a product. That's all, and take the average over all samples. That's what this formula is saying, right? So take the ith column you know, so the ith column here and the jth column. I'll subtract respective means that I can do. And then what will I do with these entries? I have to simply multiply for each row and take an average over all rows. Yes?
Yes, sir.
Okay. So if you forget for the time being these expectations, then the answer is very simple, right? You just have to take the ith row and the jth row and multiply the corresponding entries and then simply take an average. Yes? Because if you ignore the expectations, then it is simply expectation of xi xj. This is called the correlation. Right? So by the way, I don't know if here is another way of writing covariance. So it is expectation of, so I can expand the product. It will be xi xj minus xi times expectation of xj minus xj times expectation of xi minus expectation of xi into expectation of xj whole bracket, right? But what is this equal to? This is simply equal to xi xj minus, this will become, you know, there will be 2 times minus expectation of xi expectation of xj plus once, this is plus 1 time, so you'll basically get minus this. So this formula also you may remember, right? So this formula is easier to estimate. You should simply take, for estimating this, what should you do? You should take the ith column, jth column, multiply the corresponding entries, that will give you numbers, and then you take the average of these numbers, right? That's what will give you this estimate. Is this clear? And then how will you estimate this? That is already given, right? So you already estimated this, already estimated this, just multiply those numbers. So is this clear to everybody? Okay, I'll explain in the terms of the data also. So this is, what is this column representing? This column is representing various values taken by the random variable xi, right? When I did multiple random experiments, right? I did my random experiment m times. So what are the columns? Ith column representing simply the values the random variable xi took. Similarly, what will be xj column? That will be the values the random variable xj took, right, in my various repeats of my experiment. Now somebody asked, how will you estimate expectation of xi xj? What will you answer? It is simply take all the values of xi xj. What are the values of xi xj? I'll multiply this value. I'll get some value. I'll multiply this ijth value and I'll get a value. I'll multiply these, I'll get a value. Right? So that's the values. These are the values the random variable xi xj takes. So this column represents the values xi xj random variable takes. And how will you get the expectation of that random variable? Simply take the average of them. Average of them will give you what? Expectation of xi will approximate the expectation of xi. Is this explanation clear now?
Yes, sir.
Yes, sir. With if you guys are not following, I can explain it in different ways. So this is simple, right? Is it because it is simple you are not responding, or is it too tough? Okay, so I have now no choice than stopping the lecture because nobody seems to be interested. Okay, so please go back and revise all these things. next time I will use these things to talk about a generative model for regression and classification.